Hi Monojit, welcome to the live session. We'll wait for a few minutes before starting. We'll wait for 3 4 minutes and until the others join, and then we'll start the session.
Hello, sir. Is class happening?
Yeah, we'll start the class at 5 5.
Okay, sir. Okay, sir.
Welcome everybody to the second live session. My name is Anurag Gupta and I'm a teaching assistant. for this course. I am currently pursuing my PhD under Dr. Vardhan SKM here at IIT Madras. We'll continue where we left off last week. Like I mentioned in the previous live session, the following is the format that we'll follow for the live session. So first I'll discuss a set of MCQs. So these are MCQ questions, and I'll give you guys around 30 seconds to type in your answer. Following which, I'll discuss the MCQ question in detail. Once we are done solving all the MCQs, towards the end of the class, I'll take some general questions regarding the this week's content. So in this week, last week we'll had a few questions to discuss. So we'll continue from there. So I hope everybody can see my screen and can hear me. Kindly answer
Yes.
in the, yeah. Okay. Okay. So I'll continue. Uh, so we stopped here, question 14. So this is the question: which of the following is not true for an action potential? A. Amplitude is proportional to the stimulus. B. Ion channels responsible are ligand gated channels. C. Amplitude is large compared to graded potential. And D. Amplitude is all or none. So you guys can take 30 seconds to answer. Type in your answers and set a timer for 30 seconds. Okay, let's see what is the response. Okay, B. Mhm. Is not true. Okay. Amplitude is so let's discuss this. Amplitude is proportional to the stimulus. So we know that uh, the amplitude is as long as the threshold is reached, the amplitude is stereotypical, so it's always the same. Uh, so this is the wrong answer. Amplitude is not proportional to the stimulus. That is true for graded potentials, but not for action potentials. Uh, because if you recall, the amplitude that is generated is always the same in an action potential. Uh, so whether the initial stimulus is, uh, let's say, it just reaches the threshold, or it is way more than the threshold. Whatever is the case, as long as threshold is reached, the action potential is generated and it's always the same. The second option, ion channels responsible are ligand gated channels. This is also uh, this is also wrong. That means uh, the answer is actually voltage gated sodium channels. So channels responsible are voltage gated sodium channels, not ligand gated. And C, the amplitude is large compared to graded potentials. Yes, we can say that the amplitude is large compared to graded potentials, and the amplitude is all or none. This is also true in the case of action potentials. Uh, Either you have an action potential or you don't action potential. There's no such thing as a half action potential. So the question is, which of the following is not true? So we know that these two statements are not true. Hence, the answer is A and B. So let me just remove this. So I hope you guys understood this question. Moving on to the next question. Which of the following is an outward current? A. N plus influx. B. K plus efflux. C, Cl minus influx, D, Ca2 plus influx. So again, I'll give you guys 30 seconds to answer this question. Okay, let's see what is the response. Okay, nobody has responded. You guys can take a guess as well. You don't need to be afraid of being wrong. Uh, so I'll discuss this question. So we know that, okay, so this is, let us say this is the cell membrane, and this is the ECF, extracellular fluid, and this is the ICF. So an outward current is current flowing from inside to outside. Uh, so the flow of positive charges is the direction of the current. So in the first case, Na plus influx. So Na plus influx will be become an inward current. So this is not the answer. K plus efflux. So K plus, which is a positive charge which is going outside. So that is an outward current. So this is the correct option. Then chlorine influx. So if negative charge is going in, that means we can also say that a positive charge is going out. So again, this is the correct answer. Cl minus influx. So negative charge is going in is equivalent to a positive charge going out. So again, if a positive charge is going outside the cell membrane, outside the cell, then that constitutes an outward current. So these two answers are correct. And then Ca2 plus influx. Again, uh, this is an inward current because positive charges are entering inside the cell. So this is not the answer. So the final answer is B and C. So these two are the correct answers. So I hope you guys understood this. So flow of positive charge, the direction of flow of positive charge determines the direction of the current. So if positive charges are flowing inside the cell, that means that's an inward current, and if positive charges are going outside the cell, that means that's an outward current. Okay, so let us go to the next question. Which of the following statements is false? Uh, so you guys can read through this. I'll give you guys 3 minutes to solve this. This is a slightly tough question. Uh, so I'll just set a timer for 3 minutes. And you guys can take a guess as well. Need not be afraid of getting the answer wrong. Okay, we are done with our 3 minutes. Let's see what the responses are. Okay, nobody has responded yet. Uh, okay, I'll go ahead and okay, B E F is false. Okay, B E F. Sargam Bihari is telling B E F. Okay, let's write down that answer. Okay. Okay, so let's discuss this question in detail. Depolarization refers to making the membrane potential more positive. This is the correct statement. Okay, so if you recall, in an action potential, this is zero, and this is the resting state, and this is how the action potential typically looks like. Uh, so this part is called depolarization. This part is called repolarization, and this particular part is called hyperpolarization. Okay, so depolarization refers to making the membrane potential more positive. So you can see here we are making the membrane potential more positive, so that's the correct answer. Flow of positive charges outside the cell. Outside the cell is called inward current. That is false. Okay, that is not the correct statement. Flow of positive charges outside the cell is called an outward current. Repolarization refers to bringing the down the membrane potential towards the uh, resting potential from a positive state. So this is also a correct statement. Then uh, towards the resting membrane. So this is so if you recall, this is the resting membrane potential (REM), and here we are trying to bring down the membrane potential towards the resting membrane potential from a positive state. So this is a positive state, and we are trying to bring it down to REM. Hyperpolarization is a process of making the membrane potential more negative compared to the resting membrane to the resting potential. So you can see this is the REM, and we are trying to make it even more negative. So that is called hyperpolarization. So this is also correct. Flow of positive charge into the cell is called an outward current. No, this is called an inward current, right? We just discussed this in one of the previous questions. Depolarization refers to making the membrane potential less positive. Again, this is false. We want to make it more positive. You can see here, we are trying to make it more positive. And repolarization refers to increasing the membrane potential towards the resting potential from a negative state. Again, this is a false statement, right? This is not the correct statement. First of all, polarization making is not increasing, but it is decreasing, right? It is decreasing the membrane potential towards the resting potential from a positive state. Correct? It should be positive, and it should be decreasing. So here you can see repolarization from a positive state. We are trying to bring it down to a negative state. So this is also false. And graded potential has no absolute and refractory period. This is a correct statement. So the question is, which of the following statements is false? So this is a false statement. This is a false statement. This is a false statement. And G is also a false statement. Right? B, E, F, and G. So I think Bihari got it right. In three of the options you got it right. You missed out one option, which was G. So also G. So this is the correct answer. Okay, moving on to the next question. Which of the following statement is true? So again, I'll give you guys 2 minutes. Kindly go through this and write down your answer in the chat box. So I'm going to start a timer for 2 minutes. I'll just be back. I'll just fill some water and come back. Okay, let's see. Hello, can you guys hear me? Can you respond if you can hear me?
Yes.
Okay, okay. Okay, so let's discuss. Let's discuss this question. If you guys have the answer, you can just type it here in the chat box. Not sure about this. Okay, okay, that's not a problem. Let's discuss this question. Which of the following statements is true? Okay, so as action potential is propagated, the amplitude reduces. This is a false statement because either an action potential is generated or it's not generated. Uh, and if you remember, uh, as it's traveling around along the uh, this is a bad uh, drawing. Okay, if you remember, the action potential starts is regenerated at the nodes of Ranvier, uh, and either an action potential is generated or it's not generated. There's no such thing as reduced amplitude of an action potential. So this is a false statement. Action potential can sum up causing action potentials of greater magnitude. Again, this is a false statement because uh, the an action potential is stereotypical. It always has the for a particular type of cell, and its response is always the same. It So there's no such thing as summing up an action potential. Uh, and the third option is amplitude of stimulus is encoded in the amplitude of the action potential. Uh, this is also false. It's actually the amplitude of the stimulus is encoded in the frequency of the action potential. That should be the correct statement. Because if you remember, an action potential, uh, let me just draw it and show you. Why? Let me draw and show you why the frequency of the action potential encodes the amplitude of the stimulus. So this is a typical action potential which goes like this. Okay, and if you recall, a stimulus is applied, and this stimulus, if it is large enough, uh, uh, if the stimulus is large enough, then for threshold to be reached, then an action potential is generated. And if any stimulus is applied in this area, uh, another action potential won't be generated because uh, this is the absolute refractory period of an action potential. Okay, we discussed why this was the case in the last live session as well. However, if we this particular region is called the relative refractory period, and here if the amplitude of the stimulus is large enough, then another action potential can be generated. So for example, here if we apply a large amount of stimulus as compared to this region, right, then what will happen is another action potential will be triggered. So if we apply an action potential, if we apply a large amount of stimulus in this particular region, what is going to happen is another action potential is generated, but you can see that it's closer in time. So for example, a typical normal amplitude stimulus would generate an action potential here at in this particular region, right, like this. However, if the amplitude of the stimulus is large, then instead of uh, instead of waiting for the membrane potential to come back to REM, another action potential will be generated here itself in the relative refractory period, right? So the frequency at which the action potential is generated is higher because a larger amplitude stimulus uh, is triggering this action potential in the relative refractory period. So since the frequency of the action potential is high, this means uh, this basically encodes this basically tells that a stimulus with higher amplitude is triggering the action potential. So this is the logic behind this. So the amplitude of the stimulus is encoded in the frequency of the action potential, not the amplitude of the action potential, because the amplitude is always the same of the action potential. Then D, action potential at one site causes hyperpolarization at the neighboring sites. Uh, no, this is not true. This is not true because uh, action potential in one site, so there is an influx of sodium ions, and then these sodium ions within the neuron, they diffuse. By diffusion they go to neighboring regions and they depolarize uh, the neighboring regions. So It's not hyperpolarization, but rather depolarization. So this is also not the correct statement. It is possible for another action potential to occur during the absolute refractory period. No, it is only during the relative refractory period that another action potential can be generated. Amplitude of stimulus is encoded in the frequency of occurrence of the action potential. So this is correct. I just explained this. Amplitude of the stimulus is encoded in the frequency. So this is a correct statement. And damage to oligodendrocytes cause more damaging effects than damage to Schwann cells. This is true because we know that one oligodendrocyte uh, myelinates up to 50 axons, whereas if you recall, one oligodendrocyte uh, myelinates up to 50 axons plus, I think this is in the central nervous system, whereas one Schwann cells myelinates one axon only, and this is in the uh, peripheral nervous system. So, if one oligodendrocyte is damaged, larger number of axons or neurons become unmyelinated. So this is the correct answer. And as action potential is propagated, its amplitude increases. This is false. So the correct answer is F and G. Okay. So we'll go on to the next question. I hope you guys are able to follow that. Okay, again, which of the following statements are not true with respect to an action potential? So I'll give you guys minutes to solve this question. I'll just start a timer for 2 minutes. Sorry, I think I skipped question. Question 18. Choose the correct answer in relation to the sodium potassium pump. Okay, we are done with our 2 minutes. Let me know if you guys need some more time to solve this. It's a tough question. Okay, BCF. Somebody has responded. Uh, what about the others? Okay, G. Let me know if you guys need some more time. Okay. Okay, so I'll discuss this question now. BCF and G. So these are the two responses. Okay, so one person has told B as the answer and another as G. Choose the correct answer in relation to the sodium potassium pump. The enzyme has high affinity to K plus when its binding sites are directed towards the ICF. So let us recall that the concentrate this is the ICF and this is the ECF. The concentration of K plus is high inside the ICF and the concentration of Na plus is high in the ECF. So the sodium potassium pump is actually taking transporting sodium from inside to outside against the concentration gradient, and similarly it is bringing K plus inside the cell against the K plus concentration gradient, and it's using energy to do this. So the first option, enzyme has high affinity for K plus when its binding sites are directed towards the ICF. This is a false statement. In the E1 state, the sodium potassium pump has high affinity for sodium ions, not potassium ions. Okay. Then B is 3 Na plus ions bind to the active site of the complex. This is correct. Then the binding site of phosphate hydrolysis of ATP causes conformational change in the enzyme complex. Okay, so this is also correct. The binding sites are now oriented towards the ECF, and the affinity of the complex is also reversed at this stage. So this is also correct. Okay, because in the E2 state after the conformational change, the binding sites are now oriented towards the ECF, and the affinity of the complex is also reversed. Now the the sodium potassium pump has high affinity for K plus ions, not sodium. Then three K plus ions bind to the complex as the Na plus ions release. So it's actually two, not three, right? So this is the false statement. And Na plus ions release, this is true, but two K plus ions bind. So you should recall that three Na plus is transported outside and two K plus ions are transported inside using the sodium potassium pump. The complex again undergoes a conformational change and returns to E1 state, correct? And the K plus ions are released inside. This is also correct. The overall polarity remains unchanged after one cycle of exchange of sodium and K plus ions. This is false. This is not true. Uh, so the answer should be C, D, F, and G. Okay, so I think some of you some of you got some of the answers correct. So C is correct, F is correct, G is correct. Okay, so let's go on to the next question. Let me see if there are any questions regarding this. No. Okay, so C, D, F, and G are the correct answers. Moving on, which of the following statements are not true with respect to an action potential? Again, I'll give you people 2 minutes to solve this. So, some of the questions in your final exam you can expect at this level. Of course, some will be easier than this, and some will be at this particular level. It will not be exactly straightforward. Okay, I forgot to tell you that even this was the correct answer, right? We had chosen this also as the correct answer. Three Na plus ions bind to the active site of the complex. B, C, D, F, and G. So there are five correct answers. Okay. Okay, we are done with our 2 minutes. Uh, so let me know what your answers are. You can take a guess. Okay, nobody has responded yet. Okay, I'll go ahead and discuss this particular question. Uh, which of the following statements are not true? So, okay, you should be very careful while reading the MCQ. You can get these kind of tricky questions with respect to an action potential. A large hyperpolarizing stimulus may result in an action potential. This is a false statement. At the resting phase, the activation gate of the sodium channel is closed. So let us recall what happens in the sodium potassium uh, sorry, in the sodium voltage gated sodium channel. So we have two gates. One is the activation gate. This is the activation gate, and this is the inactivation gate. So we had discussed this in the last class. This is the inactivation gate. At the rest phase, the activation gate of the sodium channel is closed. That is correct. So when threshold is reached, what happens is the activation gate opens rapidly, and the inactivation gate starts to close slowly. So there's a time window during which the voltage gated sodium channel is open, and during this time, it allows sodium ions to travel through it. So this is a correct statement. The net effect of influx of Na plus ions and the outflux of K plus ions is the action potential. Yes, this is correct. This is a correct statement. So we let us recall that in an action potential, initially voltage gated sodium channels uh, open up when threshold is reached. So this leads to an influx of sodium ions, and then after some time, uh, voltage gated potassium channels open up, which leads to an outflux of K plus ions, and this is what gives the uh, shape of the action potential. So here till here, sodium channels are open, and then from here onwards, potassium channels open up, leading to an outflux of K plus, causing repolarization. Uh, so yeah, this is a correct statement. A sodium channel at absolute refractory period cannot be activated again because the activation gate is closed. So this is false because the activation gate is actually open during the absolute refractory period. Okay, so this is a false statement. The sodium potassium pumps are continuously working whether or not there is an action potential. This is true. So the sodium potassium pump wants to is trying to maintain a concentration gradient, and it's always working. The action potential may vary for different cells, but the same for a given cell. This is true. So the a typical action potential, uh, for example, in a cardiac cell, won't be the profile of the action potential won't be like this. It's slightly different. But throughout all the cardiac cells, the action potential profile will be the same. So this is correct. Myelination helps in increasing the amplitude of the action potential. This is a false statement. It helps in increasing the conduction velocity, not the amplitude. So a very high stimulus can produce another action potential even when the sodium channel is still in relative refractory period. Yes, a high amount of stimulus can produce an action potential even when the membrane is in the relative refractory period state. That is true. That's a true statement. So finally, which of the statements are not true? G is not true. Then A is not true, and D is not true. So these are the this is the answer: A, D, and G. So let me know if you have any doubts regarding this. Okay. Okay, so I'll move on to the next week two's MCQs. We'll start discussing the week two's MCQs. So neurotransmitters are often stored in vesicles, microtubules, endoplasmic reticulum, and the synaptic cleft. So let me know what your answer is. This is a straightforward question. So I'll give you guys 15 seconds for this. Let's hear what the answer is. A. Okay. Somebody has responded. Okay. Time's up. Okay, two people have responded A. Yeah, that's the correct answer. Neurotransmitters are often stored in vesicles. So if you recall, this is the axon terminal. Uh, an action potential travels through the down when towards the action potential towards the axon terminal, and here we have vesicles which store neurotransmitters. So if you recall, we have what is it what is responsible for storing this particular packing these particular neurotransmitters into vesicles. So in this case, we will only discuss about the neurotransmitter acetylcholine. So CHAT, choline acetyl transferase, is what combines choline and the coenzyme A. If I'm not wrong, I think this was the equation, but let me check once. Yeah, so it's choline and acetyl coenzyme A into ACH, and then this is packed into vesicles. So yes, A is the correct answer. Going on to the next question. Neurotransmitter release occurs through a process called as excitation contraction coupling, exocytosis, synthesis, synapsis. So again, 15 seconds. This is a straightforward question. So let me remind you, let me inform you of some of the important topics in this particular week. One is the neuromuscular junction, uh, and the process through which the neurotransmitter is released, and another action potential is generated in the muscle fiber. So this is an important topic that you need to know. Then you need to know about all the various neurotoxins that can affect this process, and also excitation contraction coupling is an important topic, and sliding filament theory. So these are the four important topics in this particular week. Of course, there are other important topics as well. So kindly don't ignore the remaining topics. Okay, let's see what the answer is. D and B. Okay, D, B. Okay, so the answer is B. So let us recall what happens. As an action potential travels, we have Ca2 plus voltage gated calcium channels, and these get opened up, and there's a large influx of Ca2 plus, and then on the vesicles we have uh, this particular uh, uh, sensor called synaptotagmin, and this detects this high increase in calcium. Uh, and once this is detected, what happens is vesicles start moving towards the uh, presynaptic terminal, and they dock onto the presynaptic terminal. They actually fuse onto the this membrane here uh, with the help of snare proteins, synaptobrevin and syntaxin, and they open up towards the outside, and they release uh, the neurotransmitter ACH by a process called exocytosis. So this process is called exocytosis. Following is the correct order involved in the release of neurotransmitter. So I just gave you a hint to about the answer. So again, I'll give you people 30 seconds, rather 45 seconds. Kindly type in your answer. Okay, let's see what the response is. C. Okay, somebody has told the answer is C. Okay, so let's go through this question. Uh, Ca2 plus voltage gated channels open in the end bulb. Acetylcholine vesicles are fused to cell membrane. Action potential travels towards the axon terminal. So this is the first thing that happens. Then calcium Ca2 plus voltage gated channels open in the end bulb. This is the second thing. Acetylcholine vesicles Ca2 plus binds with acetylcholine vesicles. This is the third. And acetylcholine vesicles are fused to the cell membrane. This is the fourth. So the answer should be 3, comma 1, comma 4, comma 2. 3, 1, 4, 2. This is the correct answer. Yes. So I think Bihari got it right. Let's go on to the next question. The presence of calcium in the end bulb is detected by the protein. So you can go ahead and answer this. Again, 30 seconds. This is a straightforward question. Okay, let's hear what the answer is. B. Yes, that's the correct answer. So this can be slightly confusing because we have three synaptotagmin, synaptobrevin, syntaxin. So this can be confusing, but let's recall that these two are the snare proteins, and this is responsible for docking of the vesicles onto the cell membrane. Uh, However, synaptotagmin is responsible for detection of an increase in calcium, right? So, question four is the option B is the correct answer. And acetylcholine is what is packed inside the vesicles. So that's out of the question. That option. Once released into the synaptic cleft, neurotransmitters produce signals in postsynaptic neuron by A. Entering the postsynaptic neuron, B. Attaching to vesicles, C. Binding to presynaptic receptors, or D. Binding to postsynaptic receptors. So you guys can answer this question. Sorry about that. The connection got lost. Let me just share my screen again. So, which is the answer? You guys can type out your answer. D. Okay. Okay, let's discuss this. Once released into the synaptic cleft, neurotransmitters produce signal in postsynaptic neuron by binding to uh, entering the postsynaptic neuron. No, the neurotransmitter does not enter the postsynaptic neuron. Attaching to vesicles. No, it is the vesicle that is released. The vesicles release the neurotransmitters. So that's also not correct. Binding to presynaptic neurons, no. It has to do something with postsynaptic, correct? So presynaptic receptors is the wrong answer. Binding to postsynaptic receptors, this is the correct answer. So we know that ACH binds to nicotinic cholinergic receptors, right? And this once it binds, it's like a lock key mechanism, and the cholinergic receptors is the are the lock, and the acetylcholine neurotransmitter is the key which opens this lock, following which there's an influx of sodium causing an end plate potential, an increase in the end plate potential. So this is the answer. Okay, so it's 6-2 right now. We'll stop the session. We have around 20 more questions to discuss. So we'll discuss this in the next class. Uh, I hope this session was helpful. So we'll meet next week. Okay, thank you, Bihari. Uh, okay, guys. If you have any questions, you can ask me now, or else we'll meet up next week. Thank you, Jyoti. Okay, bye.